Welcome back to Probability Compound Events. What's that up here? Compound events. Oh well, that's a fairly simple idea in actual fact. It's when we've got more than one event combined together and seeing how the results are going to come out of each of those events together. Okay, oh, what's going on here? Get out of there. Somebody's trying to take some discs. We need those later on in this presentation. Let's have a look around the screen now. Can you see we have got some descriptions here really of situations where there is more than one event involved. First choice and second choice of something, maybe taking discs or something out of a bag like this one here, or two spinners. So what we're going to do is to have a look at the results of two separate events combined together and whether one affects the other and how you work everything out when you've got that compound situation. Okay, so let's have a go now at clarifying some of the situations that might be involved. Here we are, we have a coloured spinner and a numbered spinner. What's the probability of getting something like a red and a 3 when you spin those two? And would they be independent? Would the result on one affect the result coming from the other? What about drawing here a disc from A and a disc from B? Discs from two different jars, two different results now. So that's what we're going to call a compound event. Okay, so let's have a look at some situations and see if we can work our way around how to work some stuff out there. Okay, here we are. This is the first one, and I said tree diagrams were going to be important, and they are very, very important to get your head around combined events or compound events. So here's our jar problem. Jar A's got some red and some blue discs. Jar B's got some blue and some green discs. So our tree diagram will start at a point and go to the first event was what? Drawing out of a jar. You could choose jar A or jar B, and having chosen jar A, you could choose a red or a blue. So what would be our outcomes over here? Our sample space will be AR, AB, or jar B with a green, jar B with a blue. Okay, coming along this pathway to there. Okay, so this is an important use of a tree diagram. It's very useful there. And then we can work out the probability distribution. What are the probabilities of each of these things? You might have done some of this before, but this is the subject of this presentation. I'm going to assume you know nothing except the basic ideas from that first presentation. I hope you've seen that already. Okay, let's go and have a look at now I'm taking screen clippings again here from Pearson's, and you might remember from the first presentation, example 7, it's a striking fact that when people create codes for their cell phones, the first digits they're talking about follow distributions very similar to the following one. In other words, some numbers from 0 to 9 are more popular than others, and there's the probability, and remembering now the sum of those probabilities should equal 1, because there aren't any other outcomes for choosing the first digit for your cell phone locking number. Okay, all right, so what were we looking for there? There were two events. First digit is more than 5, and the first digit is also an odd number. So we have this diagram here. Let's just check it out. Okay, so B is digits more than 5, so it starts at 6, 7, 8, 9. C is the first digit, is an odd number, so it's 1, 3, 5, 7, 9. And of course, there is an overlap here, or the two events intersect. You can see it more clearly on a diagram. You could have event B and event C occurring, and this is called the intersection. Okay, and it's denoted by the symbol B, like an upside down N for intersection. It doesn't start with an N, mate. Oh well, doesn't matter. B intersection C. And that's the event containing all outcomes common to B and C. So the Venn diagram here is very helpful in seeing why we call it an intersection, the items, the outcomes common to both events. So you can see we're starting to combine or have a compound event. Just remembering there are 3 outcomes to make up the total sample space, should have in that S, we'll call that big box is S, or in IB notation we can use universal set, meaning all the possibilities. So what is the intersection? We're not going to work out the probability yet. We'll do that in a minute down here. But the intersection is the set of the 2 numbers 7 and 9. That will satisfy both events. How could we work it out? Well, go back up here. We can simply go to 7 and go to 9 and add those 2 up and work out the probability of getting this intersection in here. It'd be probability of a 7 plus probability of a 9. So that's very basic approach to the problem. We're going to build on this now. So I want you to try to remember this symbol B intersection C means, or BNC means intersection of the 2 sets of outcomes, the outcomes which constitute event B, and the outcomes which constitute event C. Okay, and remember, Venn diagrams are very friendly and useful here. Let's go down and build up some more ideas. Let's have a look at another thing to do with this same combination of these 2 events, and that's now called the union, and that's U for union. The upside down N isn't really an upside down N, but the N symbol for intersection is the other one that you must know. So this is the union, and as it suggests, we want the event containing all the outcomes that belong to B or C or both. We want to unite these 2 events, if you like, the union. What are we going to do there? B union C is everything in here, all of them. Okay, we want the probability of getting any of that. Okay, so let's have a look. Could you just add up the probability of B and the probability of C? Oh no, that'd be dangerous, wouldn't it? Because see, this intersection in here, the 7 and 9 are a member of B set, and 7 and 9 are also a member of the C set, or they are part of event B and C. So if we just came down here and added these 2 up, this number, 0.103, which is our probability of 7 and 9 from just what we did with the intersection, we would have counted that in here. It would be part of this number and part of this number, wouldn't it? So we've got to subtract 1 lot of it so we don't count it twice. Okay, we include the intersection B and C, but only once. Okay, we can't count it twice. So when you want the OR rule, if you want B or C, that's what we're going to call it, the OR rule. We want B union C, B or C, or both. We want to include everything in there. We can't just add up B and C, because both of them contain the overlap or the intersection. Okay, so are you getting your ideas right there with the idea of union, uniting all possibilities of the 2 events, and watching out for the intersection, that you don't count it twice if they have an intersection. We're going to get into all of this in a minute and have a look at different examples. Okay, come on down. Let's have a look at the next rule here from Pearson's. For any 2 events, A and B, probability of A union B is the probability of A plus the probability of B minus the intersection. We don't count it twice. We do count it though. Don't count A intersection B twice. That's important. So we've got to check, do they intersect, do they both occur together? And here, as you see from the diagram below, A intersection B has been added twice, so the x one is subtracted. So in other words, if you add up A and B, there would be two of those. One in the A set, one in the B set, pull out one. Not a bad diagram. But please keep in mind, you are still including the intersection, but you don't want to count it twice. Okay, now, if there's no intersection, right, they don't overlap, what would that look like? It would look like this. And this could be what? Odd numbers, what could we say here? Odd numbers less than 5 and numbers greater than 5. So this would be 6, 7, 8, 9, like set B from before. This would be 1 and 3 only, and 5 is an odd number, but it's not less than 5, so 5 would be out here. And what else would we have? 2, 4, 6, 8. I think that covers it all. Oops, no, 6. Sorry, 6 and 8 are in that set B. So we'd have 2 and 4. So we could make up two events. We call this one maybe event A, this one event B, and there isn't any intersection here. The intersection would have 0 probability, so it's just the sum of the two there. So these over here are called disjoint or mutually exclusive. So you've got to work out when you're using the rule whether there is an overlap. Otherwise, there is nothing to take away. Are you getting the idea? Let's practice some. Okay. Well, let's have a look now at the AND rule. We want two things to both occur. That's the intersection, isn't it? A coin is tossed and a die is rolled simultaneously. This has come from Hayes and Harris, little example from their textbook. Find the probability of tail and a 2 result. Okay, a coin is tossed and a die is rolled simultaneously. So the probability of getting a tail and a 2, probability of a tail times probability of a 2. They're separate. One's not going to affect the other, so we can just multiply the two together. Okay, we want a tail and a 2. So these are independent only if you know that when one of them occurs, it doesn't change the probability of the other. So you can see here, the coin doesn't affect the die result. So the multiplication rule for independent events is the probability of both of them occurring, the intersection, is probability of A times probability of B. Alright, so we've got a couple of rules now. You may have come across these before. Let's go on and have a look. Let's do a couple of examples here. Example 8. Reconsider the situation with a traffic light at the beginning of the chapter. This is from Pearson's. The probability that I find the light is green is 30%. What's the probability I find it green on 2 consecutive days? Okay. Now, if you say it's random, you're going to say the probability of a green is always equal to 0.30. Okay. If it turns green on one day, it does not influence turning green on the next day. Okay, so they're independent, we're saying. That may not be true. They might have some timing device for peak hours and so on. But anyway, we're going to say that the two are independent. So green the first day and, keyword, green the second day, you multiply probably green the first day by probably green the second day, which is 0.3 by 0.3, which is 0.09. And you could keep going for many days. What's the probability that it's green on 5 working days in the week? And we'll come up with that answer. Assuming that they are independent, that one doesn't affect the other. Okay, so we're starting to bring in this independent idea, and this is the AND rule, isn't it? This day and this day and this day. So it's really the intersection of all days of the week. Monday, intersection Tuesday, Wednesday, Thursday and Friday. That idea. Okay. All right, so are you getting the hang of using these probabilities for more than one event, combined events or compound events? That's important. Let's have a look at this one. Computers bought from a well-known producer require repairs quite frequently. It's estimated that 17% of computers bought from the company require one repair job during the first month of purchase. 79% will need repairs twice during the first month, and 4% require, 7% require repairs twice during the first month, and 4% require 3 or more repairs. What is the probability the computer chosen at random from the producer will need no repairs, no more than one repair, some repair, and then doing two computers, combining them now? Okay, let's work through this problem now and come down to the solution. All the events listed are disjoint. You can't have the two together, or mutually exclusive, the IB tend to use. Okay, so you can't get overlap here. You, hang on, we'll just put this up here. Oops. Just come down here now. Okay, so 17% bought from the company require repair in the first month, and then twice or 3 times. So they're in one group or the other. All right. What could we say here? No repairs. Probability of no repairs is 1 minus some repairs. Okay. That's the easiest way, okay, of doing it. Not to try to list down no repairs. It's 1 minus all these probabilities of having some repairs. They are all the repair ones. So no repairs is the complementary event. Complementary event. And we'd call that A dash, if you like. If you're calling this some repairs, the event A dash is no repairs. Now, probability of no more than one repair. Okay. That's no repairs or one repair. Okay, so it's this one, no repairs, plus one repair. Okay, and you can't have the two. They're mutually exclusive, if you like, so you can simply add them up. You don't have to worry about counting the intersection twice. Probability of some repairs means 1, 2 or 3 or more repairs, so it's the sum of them all, which is what we had up there, of course. Okay, so you've got to work through what I call event analysis. Okay, this is very important, because what it looks like is that this is just one thing. No repairs. It looks like that is just one thing. You've got to really pull it apart as to what does that mean. Analyse your event into pieces. And the and or rules are important. So try to work it in like we've done here. 1 or 2 or 3 or more. Working into the event analysis or event statement some words that will indicate what to do with the probabilities. So the key words are and or, because they are our rules that we've just come across now. Okay, well, part B, since repairs on the two computers are independent from one another, the multiplication rule can be used, because now we're combining these two events. Probably that neither will need repair. You bought two computers. That's the first one not repaired and the second one. So our event analysis here would be probability that first not needing repair, and there's the key word, second not needing repair. So it's 0.72 by 0.72. Imagining that these two are independent computers. There's no association about repairing one with repairing the other. We don't know anything about that. Both will need repair. Well, need repair. So this is really probability of first needs repair and second needs repair. So it's the probability of not needing repair is 0.72, probability of needing repair 0.28. They must add up to 1, of course, because it either needs repair or it doesn't. Okay, so getting the idea, keywords up here, please note that the and or ideas. Alright, let's keep going and see how you feel about some of these others now. And just a summary here from Pearson's. Do not confuse independent with disjoint or mutually exclusive. Okay, so mutually exclusive means, unlike that diagram there that I've got for the first digit again of your mobile phone, I suggested another alternative, odd greater than 5, and here odd less than 5, and here another event where a number greater than 5, so that's 6, 7, 8, 9. This time they don't overlap, so these are called disjoint or mutually exclusive. But this possibility here, they can both occur. This is non-mutually exclusive. Okay, so that's one idea that we've had so far. Can they occur together? Yes, they can. They don't exclude each other. No, they can't. Now, a separate idea is the idea of independent events. Does the chance of being in B affect the chance of being in C in either of these scenarios? So we're going to go on and test that. Can we tell or work out whether the probability of one event affects the probability of the other? If they don't, then they're called independent events. So we want to unpack that. So there's two big things here in the IB and in probability in general, and that is the idea of intersection of two sets. Can they both occur together, or do they mutually exclude each other? And then the idea of, are their probabilities dependent upon each other, or independent events? And so independent means that knowing one of the events occurs does not influence the probability of whether the other occurs or not. Two ideas. Try to get your head around that. We're going to build on those right now. So come on down. Let's have a look. Here's the idea of conditional probability. So here's our bag. This one is taken from Hayes and Harris textbook. Suppose that a bag contains 5 blue discs and 3 yellow discs. One disc is selected at random and put to one side, not put back. A second disc is then selected from the bag. Let A be the event that the first disc is blue, and B be the event that the second disc is blue. Now if A occurs, what's left in there? Only 4 blue discs remaining, and we didn't put it back, so that's 4 out of 7. Whereas at the beginning, our chance of getting event B was 5 out of 8. Now, if A doesn't occur, the probability of B is now, well, A must have been a yellow one, so we had 5 blue discs remaining out of 7. Can you see, if you don't put it back, put to one side, if you don't put it back, all the probabilities change, and that hence the name. They are not independent, they're conditional. Probability is not independent of what happened first, it's conditional on it. It's changed, hasn't it? You've got to adjust the probability because it has been affected. So this is not independent, they are dependent events. If something happens the first time, because you didn't put the disc back, it's going to affect what happens on the second draw. Okay, fairly simple idea there, I think. You might just go over that and read that for yourself there. If you don't put that disc back, then it's going to affect the probability of things. Okay, so here it is. Here's our definition. The multiplication rule. Given any events A and B, the probability that both events happen is given by the intersection, We want A and B to occur, so A and B, you multiply the AND rule. But look out, we've changed things. We look at this symbol here. We have changed the probability of A. Okay, we've got the probability of A given that B has occurred. Okay, so if something comes first, in this case, in this definition, we're saying B has been done, and it's a probability of B times, hey, we've got to adjust the second one. Here, we've got to adjust A, given that B has occurred. This is called the conditional probability. The probability of A given that B has occurred. So we've got a symbol for it. So can we just times them like we did in an earlier example? No, not necessarily, unless they're independent. So you've got to check whether you can just times the probabilities or whether you have to adjust one. Okay, so you must know whether these events are independent. So we're going to go on and have a look at that now. Alright, so here's an example. A public health department wanted to study the smoking behaviour of high school students. They shouldn't be doing it at all. They interviewed 768 students from grades 10 to 12 and asked them about their smoking habits. They categorised the students into 3 categories. Smokers, more than one pack of 20 cigarettes a week, terrible. It's occasional, 1 pack, and non-smokers. And here's the results. So, in male and female. So smokers, 127 male, 99 female, total 226. Occasional, 73 male, 66 female, total 139. Non-smoker, 214, 189, total 403. So overall there's 414 males, adding up this line, and 354 females, so the total of all the students was that. Now here's some problems. If we select a student at random from this study, what's the probability that we select a girl? Well, let's look at how many girls there are out of the total. Female here, this line. So the total number of girls is 354 out of 768. So that's not too bad. Okay, so we could change that to 46.1%. Okay, just come down here a bit. Okay, what about a male smoker? Okay, what does that mean? We want male and smokes. Okay, so where is it? This group up here. So it's 127 out of 768, or 0.165 or 16.5%. Non-smoker. Well, it's any of this group here, isn't it? So it's 403 out of 768. So we can work some probabilities out from a basic table and using our old idea of NE over NS. And we've got all the combinations there that we just choose from. We'll do some harder ones in a minute. Here we are. In the above example, what if we know that the selected student is a girl? Does that influence the probability that the selected student is a non-smoker? Hey, they're saying it does. Knowing that the selected student is a female changes our choices. The revised sample space is not made up of all students anymore. It's only the female students. Okay, so here we are. The chance of finding a non-smoker among the females is 189 out of 354. There is a changed sample space. Let's go back and have a look at it. Let's go up here a little bit. Okay. So if we're choosing females, let's just tidy this all up again. So we'll tidy this up. If we're choosing females, there's, we know, we're just choosing females. So it's out of 354. And what do we want? Non-smoker. So it's 189 out of 354. We're not going to take this whole bundle anymore because we're choosing female. We know something about it. We have a condition on which to work here, conditional probability. So we're going to adjust it. Okay, it's going to be 189 out of 354. Okay, that is 53.4% of the females non-smokers, as compared to 52.5% in the whole group. So this is called a conditional probability, working out something with a changed sample space. And we designate it probably of non-smoker, and we read this sign as given that, given prior knowledge, given that, or given the condition that they were a female. So you go to that set and you only look at that reduced sample space, changed or reduced sample space. Okay, so you've got prior knowledge there about it being a female. You look at a different set. So getting the idea. So here, this is not independent then. Okay, you do change your probability of smoker, non-smoker, etc., depending upon the gender, because the two genders don't have the same probabilities of those groups. Okay, getting interesting? I hope so. We read this here, we just finished this off. Probability of selecting a non-smoker given that we have selected a female. Okay. And I like to say it a little bit differently from this. A, given that B has occurred, probability of the event A updated. No, I'd like to use the word that we do mathematically, conditional on. That's why it's called conditional probability. We're introducing a condition. That is, B has occurred, and has that affected whether A will occur? And we've got to seek that out, not presume they are just independent. Okay, come on down. Here we are. Here's some statements. In this case, let's look at A and B. They're disjoint sets. They're mutually exclusive or disjoint, separated, mutually exclusive. So, what does this say? What's the probability knowing that B has occurred? Well, if B's occurred, you're over here. And what's the probability of getting A? 0. Okay. What about if B is contained within A? Okay, like this diagram here, B is actually a subset of A. It's a subset of A. Okay, so what's the probability of A given that B has occurred? Well, if B's occurred, it's in this group here. And so automatically it's in A, therefore the probability is 1. So they're interesting special examples, aren't they, of conditional probability, saying that when you put this stroke there, you're saying that B's occurred. So you're reducing the sample space each time. Okay, so over here, given that B has occurred, you're reducing the sample space only to this one. Therefore, it's not possible for A to occur. Getting the idea? I hope you are, particularly from a Venn diagram. That's very helpful to get your head around this. Okay, let's do another example. This one's from Hayes and Harris. In a group of 25 students, 15 like milk, 17 like iced coffee, and 2 students like neither, and 9 students like both. Let's see if we can put this together. First of all, a group of 25 students. There are 2 outside. And they use the universal set here. So 2 are outside M and C. 15 like milk, M for milk. Okay, so there should be 15 there. So I'll write 15, and 17 like iced coffee. But 9 like both. So that in the middle, I'll take 9 away from 15 and get 6. And I'll take 9 away from 17 and get 8. So that's the first little trick with a Venn diagram. You must find the overlap, and here they tell it to us, and take that many students away from both the sets. So that, and then check it. 6 just milk, 9 like both, 8 like just iced coffee, and 2 outside don't like at all. So did that come to 25? Yes, which checks. Okay, so that's the way to do it. You must add them all up. So if they don't give you the intersection, let's say they just said 15 like milk, 17 iced coffee, and 2 outside, how would you get the intersection? 15 and 17 is 15 and 17 is 32, and 2 is 34. Too many. We've only got 25. take it away, that's how you get the intersection. Add up the two sets and see, and the one outside here, and see how much they exceed the total number of students, and that will get that intersection for you if they don't give you that. So, now, what about likes milk? So we've got 15 of the 25 students. That's, I'll just tidy this up a bit, I think. So that's this group here. Milk are any of these. So it's 15 out of 25. Of the 17 who liked iced coffee, likes milk, given that he or she likes iced coffee. Given that, that's conditional. So we've got to reduce the sample space. We've got to go just to iced coffee. That's this one. We can only play in here. Get the idea? We know that she likes iced coffee. What's the chance of liking milk? It's that 9 there. We're also in the milk likers. So milk given likes iced coffee is 9, not out of 25 but 17, due to the condition that we've placed on the probability. The condition is you must work with the iced coffee likers, because given that she likes iced coffee, reduce the sample space. Reduces S, doesn't it? You're not looking at the whole 25 anymore, you're zeroing in on that group. So Venn diagrams are very important to see what's going on in reducing that sample space. Okay, let's look at another example. In psychology lab, researchers studying the colour preferences of young children. 6 green toys and 4 red toys, identical apart from the colour, are placed in a container. The child is asked to select 2 toys, so we've got compound events. What's the probability that the child chooses 2 red? Now here's a tree diagram for this one is useful, because you've got 2 choices, first choice and second choice. So start off with a dot. First choice could be a red or a green. Look at this introduction here. The probability of getting a red is 4 out of 10. Yep. Probability of getting green 6 out of 10. Now, you're not going to put it back. They get a choice of 2 toys. So when they take one out, they're going to keep it. So what's on the second choice now? How many red have we got? 3, and the child didn't put it back, so it's out of 9. What have we got for green on the second choice, given that we chose a red? There's still 6 green, but they didn't put it back, so it's 6 out of 9. So all these second choices are all conditional probability. They are all affected by the first choice, conditional on the first choice, because even if it's not the same colour, you don't replace it, so the totals are going to be out of 9 everywhere here. So if you have chosen a green, then you've still got 4 red, but only out of 9. If you've chosen a green, you've only got 5 green left out of 9. Okay, so let's work out the probabilities of each of these outcomes down here. A red, given that a red has been chosen, that's a red, times the probability of a red given that the first was a red. So all of these here, all of these are the probability of something given something else has occurred. Let's do the one that Pearson's has got down here. What have we got? What's the probability that the child chooses 2 red toys? So there it is, red and a red. The top one, that was the one that I just did. It's actually the probability of red and red, probability of red given red, that one, and also red given green. Okay. Oh no, hang on, what have they got here? We're interested, oh no, we don't want that one. We only want the first one, as I've got it here. So probably a red times probably red given red, that has been adjusted because there's 1 less toy and 1 less red. So it's going to be, and they've gone to percentages now, just to give you flexibility between decimals and fractions and percentages. So this one here, as I said to you, was a probability of a red given that a red occurs, this little one in here. Well, that one's been adjusted. Are you getting the idea? So we've got to keep our wits about us. Has to have things changed. You can't just say the probability of red is always 4 out of 10 as it is at the start, because we don't replace it. The second event here, or the second choice, is conditional on the first. All right, think through that one. You might like to go back, rewind the presentation and check it out. So here we are. We've got, if the probability of an event is not equal to naught, conditional probability of A given B is this, and we adjust it. Where did this come from? Yes, I think we can see that in a minute. We'll do it differently though. Let's see if we can understand this rule, because this is used by the IB quite a bit. The probability of A given that B has occurred. A given that B occurred. That's what we want. Let's do it. Hang on, another R in there. Let's do it from the Venn diagram. Now we know that B's occurred. So it's somewhere in this group here. Reduced S to B. Haven't we? Reduced the sample space to just a set of B, because we are given that B occurred. Okay, so B has occurred, so we're in this group B, and we want to know the probability of A occurring. There's only this little bunch in here. Alright, that is also in the A set, knowing that they've got to come from the B set. So that's the idea, isn't it? The probability of A given that B occurs is this group. The probability of the intersection out of probability of B, not out of S anymore. It's reduced. So you can think of it that way. That's what we've just been doing, taking the intersection number and dividing by B. Okay, and we've actually been doing it in numbers, because here what we've counted up was the number in the intersection over the number in B, which is what this comes to. Probably the intersection here is number in the intersection divided by NS over probability of B is a number in B divided by NS. And if you invert and multiply, they'll disappear. And so you can work with the numbers or just the probabilities of those two, dividing those probabilities. And of course that goes back to our other rule. The probability of an intersection A and B occurring is the probability of A given that B has occurred times the probability of B. So it's a rearrangement of that one. So there are many ways in which the IB wants you, or in probability in general, to work out conditional probability, that thing there. You might actually use this rule, or you might just suss it out. Did the child replace the toy or not? Or you might use a Venn diagram and numbers. So there's lots of ways of thinking about it. Okay, let's keep going and see what you think now. Here's a little bit of a problem. I've done a little bit of work on this. One's not from Pearson's. I've taken their table. Here are smokers and non-smokers. Different one again now. Male and female smoking regularly, occasionally, or not at all. Okay, so what's the probability of a non-smoker given that they are females? This is harder because it's all probabilities. So let's go and look at it. Probability of a female is, that's a smoking female, don't want that yet. Probability of a female is along this line, isn't it? Probability of a female is going to be all of these added up. Okay, here it is here, and we want a female, a non-smoker given that they're a female. So what is it? It's this group out of the female group. This is reduced again. We've reduced S. Or this is the rule, if you like. The rule that we've just had there. Probability of non-smoker given that female equals probability of non-smoker intersection female over the probability of female Okay, so here female and non-smoker is the intersection, which is this group here. It's got to be a non-smoker and a female out of the total here. This is probability of female in the whole line. For the sum here, I'll put this in. We'll put the sum of that line is probability of a female. It's all in probabilities now. So you have to use this rule, if you like, the conditional rule. Probability of a non-smoker given that they're female is probability of a non-smoker and female divided by the probability of a female. And here we have that conditional probability. So you've got to keep your wits about you. Think about it in various ways, but it's a reduced sample space, isn't it, that we're on about here. Okay, come on down and let's have a look at another Pearson's example. This is male and female, colourblind or not colourblind. Not being able to tell the difference between green and red is colourblind. Okay, collected information on 1,000 people in a small town and divide them up into colourblindness and gender. And there's the findings. What is the probability the person is colourblind, given that, here it is, here's the condition, given that the person is a woman? Okay, so we're looking at the person being a woman. Okay, let's have a look at their solution and see if we agree with a way of going about it. We do not have to search the whole population for this event because we're given a condition. And the condition is women, given that it's a female. Something/female. We have 490 women, so we can do it on numbers now. It's a reduced sample space, reduced S. All of these things we expect. Once we're given that. We're given that. Yeah, we're given the condition. Okay. So, then we search for colour blindness. We only look for women who are colourblind. That is the intersection. And here, out of females, there's only 2 colourblind. So it is 2 out of 490 on numbers. Okay. Or you could use the rule, colourblind given that it's a woman. Well, I would have called female because it's entered as female up there. But anyway, it's a probability of colourblind and a woman, which is that 2, divided by the probability of a woman. And that's just the numbers. We go to the numbers there. That's what we were saying before. You can work with probabilities or numbers. This is numbers, so I had back in the other one it was probabilities. Okay, notice that here we use the frequency rather than the probability because that's easier. And they've done the same sum as I have. That's been all messed up there. So in other words, the probability rule is the probability of the intersection, which is that over that, divided by the probability of a woman, which is that over that, and the NS's invert and multiply, they would cancel. So you can either work with a probability of the intersection divided by the probability of a woman or a female, or you can work with actual numbers. Okay? Are you flexible enough here? You're getting interesting, isn't it? Okay, let's look at example 13. AUA, a national airline, are known for their punctuality. The probability that a regular scheduled flight departs on time is 0.83. The probability that it arrives on time is 0.92. And the probability that it arrives and departs, so that's the 2 together, the intersection, is 0.78. Okay, all on time. Find the probability that a flight arrives on time, given that it departed on time. So, what can we do with that then? Arrives on time given that it departed on time. Okay, so let's use the rule here. The arrives on time given that it departed on time is the probability that it arrives on time and departs on time, divided by the probability it departs on time. So we've got all those. Probably arrives on time and departs on time, divided by the departs on time, which is 0.94. So we're using the rule there. In general, that probability of A, given that B has occurred, is the probability of A and B occurring divided by the probability of B, reducing the sample space here. Probability the flight departs on time, given that it arrived on time. Okay, departs on time, given that it arrived on time, is the probability of departs on time and arrives on time divided by the probability that arrives on time. So these two are the same, aren't they? Departs on time and arrives on time is the same as this one. So we're given that 0.78 and dividing by 0.92. So again, the IB do like you to be able to use this rule. It's the hardest example of conditional probability. We can't draw a Venn diagram very easily to describe it. You can't count up the numbers in the two sets and that sort of thing. So be able to use that rule, that's important. Okay, let's summarise independent events then. Independent events is when the probability of A, given that B has occurred, doesn't change. It's just equal to the probability of A. Two events are independent if the probability of getting the two is the separate probabilities. No adjustment here. No adjustment given that one has occurred. Hang on, I'll just do that better than that. No adjustment knowing that one has occurred. That's what we have to test. Okay, so even if we do have a condition, the other probability doesn't change. What's the easiest way of getting your head around that? If we go back to the bag of discs, then if you put the disc back after you draw the first one, the second draw is independent of the first. It doesn't make any difference what you did on the first one. You pull the disc out, put it back, note its colour, put it back. So the events would then be independent. You would not adjust the probability of A given B. You just still stay at the probability of A. Alright, so we need to test for independence sometimes. The IB like that sort of question. Take another look at the plane situation. Are the events of arriving on time and departing on time independent? Well, let's have a look and answer it in two different ways. First way, the probability of arriving on time is 0.92, and we found that the probability of arriving on time given that it departed on time is 0.94. Since they're not the same, we found that you could, when you adjusted knowing that it departed on time, you got a different answer. So they are not independent. We don't generally say dependent, we say they're not independent. Alternatively, you could go about working out the intersection. That was given to us, 0.78. So that's the probability of arriving on time and departing on time. And then if you multiply the two separate ones together, you get 0.92 by 0.83, and therefore it isn't the same. So I think that definition is easiest. If the probability of two events both occurring, this is A intersection A and B, if they are the simple product of the two, then they are independent. I think that's the easiest one to use. If you have no adjustment of these, not adjusted because the other one has occurred, not adjusted. So if you don't have to adjust them, then, and you get the simple product equals the probability of the intersection, then they're independent. Alright, so let's have a look at example 15. Many countries, police stops drivers on suspicion of drunk driving. They give a breath test, a blood test, or both. In a country where this problem is vigorously dealt with, police records show the following. 81% of the drivers stopped are given a breath test, 40% a blood test, and 25% both tests. What is the probability the suspected driver is given a test? Exactly one test, no test. And are giving the two tests independent. Okay, I want to do this in two ways. First of all, let's come over here to this method. part 1. What's the probability is receives a test? So this is analysing your event. That's the probability receives a breath test or a blood test or both. So it's a probability. Oh, hang on, we'll just go back up there. Sorry about that. Let's come up here. Oh, went a long way, didn't we? Come back up. These are all the things we want to do in a minute. We'll just bring this down a little, come across here. Okay, sorry about that, that didn't go too well. Here, so this is the probability of the union, breath or blood, BR and BL, and we want one or the other or both. So it's a probability of the breath test plus a probability of blood test minus the probability of the intersection. You can't count the intersection twice. Do we have all those values? Yep, we had 0.81. Just come up here a little bit. Yep, 0.81. And then blood was 0.4 and 0.25 was both. So the answer is 0.96. Purely going on the probabilities. I'm not doing the Venn diagram method yet. Okay, what's the probability that receives exactly one test? Let's just come down here. Okay. Exactly one test. It's the union here. I think I've got the union there, 0.96 from here, and we have to take off that intersection. Alright, because we don't want the intersection here. We're going to take off another lot of it. Or you could just say the two separate ones, so it's 0.96 minus 0.25, so you're taking away the chance completely of having two blood tests, which is what we did here. This is one or two or both, so take off the idea of both. There it is there, we get 0.71. Okay. And what's the probability of receiving no test? Okay, receives no test, use the complement, 1 minus the probability receives a test, which was back up here. Part 1 receives a test, one test or two tests, one or other or both rather. So if they receive none, it's 0.04. Alright, so that's one way of actually looking at the problem. Let's go back up now. Oops, too far again. Let's come back up here and have a look at the Venn diagram way of doing it. Okay, the Venn diagram way says what's the probability of a test? Well, let's look at it. What has Pearson's done here? They said blood was 0.4. Okay, and that consisted of both, which is 0.25 plus 0.15, so it's broken the 0.4 down. And the breath was 0.81, but both was 0.25, so take that away. 0.56 is probability of having just breath, both 0.25, and just blood 0.015, and 0.04 weren't tested at all. So what's the probability of having a test? Well, here, this makes it a little bit easier. You don't have to use the rule that we used over here. You can add them up. It's 0.15 plus 0.25 plus 0.56. You can just do it straight like that. And you'll get the same answer, of course, 0.96. The Venn diagram is a more basic way, a non-sort of rule way of doing the problem. Exactly one test. Well, that will be either this one or this one, but not both. So it's going to be 0.15 plus 0.56, 0.81. Okay. And then what about no test? The no test is what's left out here, 0.04. Okay, so come down just a little bit. 0.04. Okay, so what about the last little bit here? Sorry about the skipping today, it's not good. Okay, are the tests independent? Well, let's use the rule here, the probability of getting them both. That's breath and blood. If they're independent, you would find A equal the probability of breath times the probability of blood. You wouldn't have to adjust them. Let's check it. Now we know that the probability of breath and blood test was 0.25 given to us. Now let's check. The probability of breath times the probability of blood was 0.81 times 0.40, which is 0.324. Uh-oh, these two don't match. The probability of breath and blood is not equal to probability of breath times probability of blood. So giving the two tests is not an independent situation. Okay, can you see that? I think this is the safest way of testing for independence. You say, is it true that the probability of getting both equals the two separate probabilities? Then go and check it. We've got the probability of both, and it isn't equal to the two separate probabilities. Therefore, one is not independent of the other. Okay, getting a bit complicated. Try to get your head around all the things that are happening. We'll do a little bit of a summary in a minute. Here we have a clipping from the IB formula book, new formula book. So let's just check out what their probabilities look like. NA over NU for the basic probability, and here the sum of A, probability of A, of getting A, and the probability of not getting A must come to 1. You must either get A or not get A. The union here, A or B occurring, is the probability of A plus the probability of B minus the probability of the intersection. So this is the AND rule, making sure you check whether they're mutually exclusive. You can't count that overlap twice. Here, if they are mutually exclusive, you don't have an overlap, so it's just A plus B. So check that out. Be careful. I like students to always try to use this one, and so they never forget to take off the intersection. Then if there isn't an intersection, if they're mutually exclusive, the intersection is 0. Right, conditional probability. Probability, they don't give you an actual formula for it, it's in there. So the probability of A and B occurring is the probability of A times the probability of B given that A occurs. Or if you rearrange this, it would be the probability of the intersection divided by the probability of A here. I'll get rid of that in. Okay, so yes, they don't have the actual conditional probability formula. You can rearrange it from this one. If they're independent, the conditional probability is 0, of course. The probability of A and B occurring is a simple product of the probability of A times the probability of B. That's if they're independent. Okay. Alright, so that's a bit of a summary. So we've got some and or rules here, and we need to try to analyse the event carefully so we can use these rules, analyse the event, break it down into words where you can do it. Okay, so let's have a look then at some problems. I'd like you to pause the presentation and try these, and as usual, down below are the solutions to these problems. So here's the first 3. Have a go, and then you might scroll forward and have a look at the solutions as you go with the problems. Don't do them all. We'll gradually go through now. So question 4 and 5. Six, 7, 8, 9, and the last few 9, 10 and 11. Okay, very important to analyse the event and see what they're really looking for. Okay, let's look at the solutions now. Question 1 and 2. Let's go down a bit. That's 3 and 4. Okay, just go to 5 now. See if we can get 6 in. Part of 6 there. Let's go to the rest of 6. Rest of 6 there. Very good. Let's go to 7. Yep, there's 7 now. Eight. 9 and 10. And 11. Alright, we see some practice questions coming up. I don't know how he went there. Now, these practice questions are from Pearson's also and summarise both presentations on probability. So that's all you have to know. So let's see how good you are. You might like to come back to this if you're getting tired. Let's have a look at the practice questions on the 2 sections. There's question 1 and 2. Question 3 and 4. There's question 5. Question 6 will just come up a bit. Question 6 and 7. Question 8. Nine, 10 and 11 there. We'll come to 13 in a minute. There's 13, a little bit of a tree diagram there. $14. 15 and 16. There's 17. $18. There's 19, 20 and 21. There's 22. $23 and part of 24 there. Just go and look at the rest of 24. $25. $26. $27. And 28. Those last ones here, if you just look down the bottom here, 11 to 28 are IB questions that they have had before in exams and so on. Alright, so let's go and look at the solutions to those 28 questions. Okay, here we are. Question 1, 2 and 3. Go to question 4 and 5. See if we can get it all on. Yes, 4 and 5. Okay, go to question 6. We'll see if we can get 6, 7 and 8 on there. Yep, 6, 7, 8. See if we can get all this on. 9, 10, 11 and 12. Thirteen and 14. There's 15, 16 and 17. See if we can get 18 and 19 there. See if we can get the rest on. 20 through to 22. Through to 25 there. (26) 27 and 28. Right, well, I hope you enjoyed that. That's a really good workout on probability, and that will prepare you well for any examination. Okay, I hope you enjoyed that. I hope to catch you in another presentation as we work further through the course, but at the moment it's cheers from me